Okay, so now we talk about set of sets. I mean, if the elements are also the sets. So, this is called set of sets. So far we have seen the elements are, I mean the set elements like real number. So, if the elements itself is a set, then it is called set of sets. Like if we take a set, say S 1 2 3. Now, if we consider set of all possible subset of S, suppose we consider set which is basically set of all possible subsets of S. So, what are the possible subset of S? Like possible subset of S. So, what are the possible subset of S? Phi is a subset of S. Every I mean null set is a subset of every set. Now, if we take a single element, these are all subsets, single element 1 2 3. Now, if we take two element together 1 3 1 2 1 3 and 2 3. 2 1 is same as 1 2, because the inside set ordering does not matter. Okay, this is just a collection. We do not bother about the ordering, whether one come first in this, it is a back, we are putting this element, that is it. So, we do not care about the ordering of this element in a set. So, set is a collection, and then just the 1 2 3. So, then the 1 2 3. So, the set itself is. Now, this collection, this is also a collection. What is this collection name? Collection name is the set of all subsets. This is a set, but element of this set is a subset of S. This is called set of sets. So, this is has a name, this is called power set of S. We can denote the power of S. This is called power set. This subset, set of all subset, this is called power set of power set. Okay. This collection is called set of all subsets. Now, so how many elements are there in this power set? So, 1 2 3 4 5 6 7 8. So, there are 3 elements here. So, power set is basically power of, so S is 1 2 3. Now, the power set is basically power of S, this is basically 8. So, this is called cardinality. So, this symbol we denote by cardinality. If we have a set, this is basically called cardinality of the set, that means number of element in A. So, this is the number of element in A. Okay. This is called cardinality of the set. Now, when we called a set is finite, if either A is empty or this cardinality is finite. If there are finite number of elements in A, then we call this set is finite set. Okay. So, this is 8. So, this is basically 2 to the power 3. So, there are 3 elements. So, it is 2 to the power 3. So, the question is whether it is true in general. If suppose there are n elements, then what is the size of the power set? What is the cardinality of the power set? So, that we will see now. So, this is the set of sets. Our set is a collection of sets. Okay. Earlier it was collection of some numbers, real numbers, this, but this is a, now we are talking about collection of subsets, set of sets. Okay. Now, say we have a set of n element A 1 A 2 A n, these are the elements. Now, we would like to know the power set of this set, power. Power set means set of all possible subset, it is a collection of all subset. So, what if phi is a subset, one every single element is a subset like this. Now, the size of this pau is 2 to the power n, that we have to show or we have to convince. Now, how to show this? Now, to show this, so let us take some symbol like x1 a1 plus x2 plus means I will define this x2 a2 plus I will better use union x3 a3 union dot 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 xn an. Now, I can say my pau is this, pau of S is basically this collection where this x1, x2, xi is either 0 or 1, xi is either 0 or 1. Okay. So, that means if all xi is 0, if xi is 1. So, this is in general here we have this term is xi ai. So, if xi is 1, so that means that subset contain ai. Now, xi's will give us the ai. If all xi are 0, then nobody in that set. So, that will give us phi. Now, if only x1 is 1, if x1 is 1 and remaining all are zeros, sorry, if x1 is 1 and remaining all are zeros. Okay. So, this will give us this set A1. Now, if x1 is 1, x2 is 1 and other than x1, x2 all are zeros, then this will give us this set union. So, basically it is a membership this whether. So, we are considering we have n elements, we are picking the elements like this. So, this is a sort of I mean who will be coming in that set subset depending on the values xi's. Okay. Now, the question is how many such subset will be there. So, that is the possible how many possible way we can choose xi's. So, xi can take 2 values each of xi's. So, there are n such. So, what is the size 2 to the power n. So, the size of this pau is 2 to the power n, because each of xi's can be either 0 or 1. So, that will give us the this 2 to the power n. So, this is the concept of the power set. This is basically a set of all possible subsets including phi and s. So, s means all xi's are 1, that combination. When all xi's are 1, that will give us s, the whole set, and if all xi's are 0, that will give us the empty set. Okay. So, this is the set of all subsets, set of sets, and in particular it is called power set. And this collection, suppose we have some collection of sets A1, A2, An. This is a collection of sets, this is a set of sets. So, we denote this collection say F, some collection F. Now, how to take the union of this? So, we can denote this by Ai's I belongs to this way also we can denote. Okay. Or if you define this I to be this 1, 2, 3, 4 up to n, then we can define this collection as Ai's where I belongs to capital I. Okay. So, this is the way. Now, we define the partition over a set using this concept of collection. This is the set collection. So, we define the partition of a set. Suppose we have a set A. A is a non-empty set. Let A be a non-empty set. Non-empty set means it is not null. There are some elements in A. Now, we called a collection if I belongs to this I, say, where I is, this is a finite collection. It could be infinite collection also. This set could be infinite also, but let us just start with the finite collection. Okay. Now, when we say this F, this is a partition on A if it satisfies this property. First of all, it must cover the whole set. So, that means union of I belongs to this must A. So, it must cover the whole set, then it is called the partition. And when it called disjoint partition, if we take any two A I and A j, any two element, then this must be empty. They are disjoint subset. For all I not equal to j belongs to this set, then it is called disjoint partition. So, that means this will partition like this. So, this is A1, A2 is somewhere, AI dot 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 AN. Okay. So, we just do a partition on this set. So, this is a disjoint partitions. Okay. So, now we define relations, and then before that let us talk about another set operation which is called Cartesian product of two sets. So, let us just define Cartesian product of two sets. So, again let us take two sets, let A and B two non-empty set. So, then how we define Cartesian product is symbolically denoted by this A cross B is basically the set of all pair A B, this is called ordered pair, such that A is coming from A and B is coming from B. This is the definition. This is the definition of Cartesian product. Okay. So, if we take all the ordered pairs from A B, the ordered pair. So, where first coordinate, you can say coordinate, or first ordered pair has two elements. First element is coming from A, this is the first element, and the second element is coming from the set B. Now, for example, if we have set say A is equal to say 1, 2, 3, 4, or let us take small one, and if we have set say 2, 5. Okay. If we have this set, then what is the Cartesian product A cross B? A cross B is basically A B all ordered pair. A is coming from, so 1, 2, 1, 5, then 2, 2, 2, 5, then 3, 2, 3 comma 5. All possible pair where first element is coming from A, capital A, and the second element is coming from capital B, all possible pairs. So, 1 can be with 2 and 5, 2 can be again from 2 and 5, 3 can be with 2 and 5. So, this is the Cartesian product A cross B. So, this is how we define the Cartesian product between two sets. Okay. Now, we know the this coordinate geometry, we know the plane real coordinate plane x y axis. So, that is nothing but r cross r. So, our in the coordinate geometry we have the points on the plane like x y plane. So, one axis is this is the axis, no, this is the x axis, this is the y axis. This is the x axis, this is the y, and any points here, this is the first coordinate. So, points are like 1, 3 like this. Okay. So, every axis is basically a real line. This is a r, this is also another r. So, this plane is basically the coordinate points are coming from r cross r. This is also this is nothing but a Cartesian product. This is a 2D plane. If we have 3D plane, then r cross r. Okay. So, this is just a coordinate. Now, we will define the relation between two sets. Relation, we define the relation. Okay. Now, how to define relations? Let us take two sets, let S and T be two non-empty set. So, every time we need to take the non-empty, otherwise there is no meaning of defining all these terms, because if one set is empty. Okay. Then we defined a relation which is denoted by rho is nothing but a subset of the Cartesian product. Every relation, a subset of a Cartesian product is called a relation. Okay. Now, what is the meaning of this? Meaning of this is basically the relation rho, we denote this by this symbol between S to S and T is a rule that associate some of the elements, some or all the elements, some or, because depending on the, this is a subset, how many, if it is equal, then all the elements, if it is not equal, proper subset, then some of the elements, some or all the elements of S with the elements of T. That is, this is a rule. Okay. Some of the elements of S is associated with the rule of some of the elements of T, then that is that is a relation. Okay. So, this is the definition of relation, but it is basically a Cartesian product, it is a subset of the Cartesian product S cross T. Now, let us take an example of a relation. So, let us take an example. So, we take two set S is basically say 2, 3, 4, 5 and T is basically some set 11, say 12, 13, 14. Okay. Now, what is the Cartesian product? Cartesian product is basically all possible pair. Now, let us define a relation rho S T belongs to rho. So, S T means, so relation means we know relation is a subset of the Cartesian product S cos t. Okay. Now, every element will be in the form S comma t. This is a subset, this is belongs to S Cartesian product T. So, if a relation is collection of all such pair, I mean a subset of S cos t. So, it is a element of rho is basically like this. So, we defined a relation on these two sets as follows. S is S t is this, otherwise we can write this as this. S is related with T with the relation rho. This also one way you can write this. If and only if S is a factor of T, if S is a divisor of T, if S is a factor of T, then we say S T is relation. So, suppose we take 2 and 11, is 2 and 11 is related with this rho? Question, is 2 is a factor of 11? No. So, that means 2 and 11 is not belongs to this rho. So, that means 2 is not related with 11 by this relation. So, not all the Cartesian, all the elements of the Cartesian product will belongs to that relation. Okay. So, now the question is, so who are the elements there? So, if we define this, then the rho is basically consist of 2 is a factor of whom? 2 is a factor of 12 and 14. So, 2 is related with both the 12 and 14, and then 3 is a factor of whom? 3 is a factor of 12. So, 3 is related with 12, and 4 is a factor of whom? 4 is a factor of 12. So, 4 is related with 12, that is it, nobody else. So, this is a subset of the Cartesian product S cos t. This is an example of a relation. Okay. So, relation is basically it is a subset of the Cartesian product. Any subset of Cartesian product is a relation, and if two elements are belongs to rho, then we said S is S is having relation with T by the relation rho like this. Okay. So, now we defined, so this is the general definition of the relation. Now, we define the binary relation, where we have only one element, only one set. Instead of two set S T, we have single set. So, this is called binary relation. Okay. So, what is a binary relation? So, we have a let S be a non-empty set. Then binary relation means basically rho is a subset of S cross S. Here we have only one set. Okay. General definition is two sets, but here we have only one set S cross S. So, this is the definition of a binary relation, then it is called a binary relation. That means, we have only one set non-empty set S, if it is if there is a. So, now let us have some example on this. So, for example, if we have say set of real number, okay, or say sorry, if we have a set say 1, 2, 3, 4. Now, if we define a relation less than, okay, the elements which are less than. So, less than means if we, so this is basically a subset of S cross S. So, S cross S means, so who are the elements are less than? So, 1 2, 1 3, 1 4 like this, because 1 is less than 3. So, that means 1 3 is belongs to this less than, belongs to this less than relation, and this is also a element in the Cartesian product S cross S. So, this is the way. Now, suppose we have set of real number. Okay, suppose we have set of real number R. Now, we define the relation equality. Equality. So, that means we take two element A B will be related with this if and only if A equal to B. So, who are the element in this? This is basically 1 1 is belongs to row, 0.5 is belongs to row, okay, but all are subset of this is also belongs to R cross R, all are subset of the Cartesian product. Okay. This R cross R. So, this is a infinite set basically, but this is the concept of the binary relation where we have a single set and we define the relation as a relation is a subset of the Cartesian product, but here the set is S, a single set. So, S cross S. Okay. So, we will discuss more of the relation in the next class. Thank you.